Shinsei. Shinsei, you can start. You're muted.
Yeah, sorry, I was muted. Thank you. So thank you for the invitation. Today I want to talk about dynamics of many-body quantum systems for out of equilibrium processes. In particular, I will choose to work with two-dimensional conformal field series. So I have a few papers on this topic. I will focus on mostly the first paper, where we discuss the so-called operator entanglement to diagnose dynamics of conformal field series. The other papers which I can mention along the way. But before that, I have a wonderful collaborators who did actual works. So Mao Tian Tan is my graduate student, graduating soon, and Jonah Kudra-Fram is another graduate student at Chicago. Rai Mei, she is a postdoc at Chicago, but she's going to at UIUC. Masahiro is another postdoc. He was a postdoc at Chicago. He's now in Japan. Okay, so type of phenomena which can happen in the non-equilibrium system, and that is interest of my talk, is the quantum information scrambling. So that can happen for system with enough complex dynamics. And it is also related to the idea of thermalization, where let's say if you start from some initial state, we eventually go to the system described by density matrix, at least locally, by the Gibbs ensemble. So what is happening here is that because of the very complicated dynamics, the information of the initial state will be completely erased, or at least will be inaccessible locally. And then it will be after some late time, the part of the system can be described by a universal density matrix, just a Gibbs ensemble. So that is an intriguing phenomena. Although quantum dynamics can be very complicated in principle, here's some universal or at least ubiquitous phenomena can emerge in non-equilibrium many-body systems. So we are interested in what kind of system can happen, can support such quantum information scrambling or thermalization. When does it happen? And then what could be a good probe for such phenomena, and so on and so forth. So that is the basic here. So for example, we could use out of time order correlator, OTOC, to diagnose the complexity of quantum dynamics, which has been studied, for example, in SYK type models in recent years. And there's also other probes, spectrum form factor, and the other quantities. But today I want to use the this quantity operator entanglement, which I will define shortly. And the operator entanglement can be defined for unitary time evolution operator, or any operators, or any local operators. So I think in my talk today, I will be mostly focusing on unitary time evolution operator of two-dimensional conformal field series. So that is this paper from 2018. In data papers, we also studied local operator entanglement. So if time allows, I will also mention that. And that is the most recent publication, the preprint listed here. So the idea is the following. So I'm interested in the time evolution or dynamics of some many-body system, quantum system. And I have a time evolution operator or some other operator. that is defined on the Hilbert space of the problem. But the operators, they can be thought of as living on their own Hilbert space. So starting from the physical Hilbert space, we can essentially double the Hilbert space, and then you can regard operators as a state in this enlarged or doubled Hilbert space. The way to see it is to start from representation of the operator in some basis, which can be written in this basis a ket b bra, but you can basically just flip this is bra, yeah, this is bra. You can flip bra to a ket, and then you can think of this this state as a state corresponding to the operator. Okay. We will be calling these two Hilbert spaces input and output Hilbert spaces, respectively. And this mapping, for example, it works for the case of unitary time evolution operator as follows. So we start from E2 minus ITH, that is the unitary time evolution operator. Quite often, it is also convenient to introduce some sort of smearing factor. So this epsilon is some sort of regulator. And then I follow this mapping, state operator mapping, and then I define the state, okay? So in many body system, or maybe in quantum field theories, I may be summing over infinitely many states. So sometimes we want to keep this regulator. It can be visualized as this box, which represent some operator, and it's input, and then it spits out output, and there's some time, the direction of the time associated to that. And the idea is that, well, at least for me, state is simpler than operator, but if I can map an operator to a state, I can use all the probes I know to characterize states. I can utilize these ideas to operators. So, for example, I will be able to study a quantum entanglement of operators, just like we define quantum entanglement from the state. And maybe quantum entanglement measure can tell us something about non-trivial dynamics of quantum many-body system. In particular, because of this structure, double Hilbert space structure, it will be interesting to study entanglement between degrees of freedom in input Hilbert space and the another degree of freedom living in the output Hilbert space. It's like a correlation between future and the past. So that can tell us something about dynamics of quantum many-body system, as we will demonstrate. One idea is to, okay, so maybe before introducing why quantum entanglement for operators are useful to characterize dynamics, I will first formally define some quantum entanglement measures. So just like states, we can define a quantum entanglement entropy for operators, which is straightforward once we have states which are mapped from the original operator. So I trace out some part of the Hilbert space, and then we get a reduced density matrix, and then we can talk about quantum entanglement. As I mentioned earlier, when we trace out the degrees of freedom, some degrees of freedom can be in the output Hilbert space, and the other can be in the input Hilbert space. They don't have to be in the same Hilbert space. Okay, that is going to be important. More precisely, we will be interested in mutual information defined for the operator. So that is defined by the combination of entanglement entropy. So this is the operator mutual information between subsystem A and subsystem B. I use this index n to specify Renyi index. And sometimes I also put 2 here to indicate that this is the bipartite correlation measure between subsystem A and B. Okay. Like I said, for the most of my talk today, I will be interested in 2 regions, one in the input and the other in the output. Okay. Another quantity, which is perhaps more useful, is the tripartite operator mutual information. So now there's 3 part of the Hilbert space. Let's say A, B1, and B2. It can be arranged in this way where I have A in the input Hilbert space, whereas B1 and B2 can be included in the output Hilbert spaces. Okay, and I combine mutual informations to define tripartite operator mutual information. Okay, to contrast with bipartite operator mutual information, I sometimes put this index 3. And as before, n is a Renyi index. Okay, right. So the idea of using this tripartite operator mutual information was, I think, first advocated in this paper by Hosachi, Roberts, Yoshida, where they propose that the negative value of the tripartite operator mutual information is an indication of quantum information scrambling. Okay. Idea is as follows. So if you look at these 3 terms, A1, B1, and A1, B2, they represent some sort of a correlation between input and output Hilbert spaces. Now looking at the 3rd term, which is subtracted, this region is so there's the B1 union B2, which is a combined region of B1, B2. So compared to the first 2 terms, the last term captures more global correlation or non-local correlation. And as I mentioned earlier, quantum information scrambling is about non-local spreading of quantum information. So if there's a non-local spreading of quantum information, we expect the 3rd term to be bigger in its magnitude, and therefore tripartite operator mutual information will be negative if quantum information scrambling takes place. That the idea was tested in this paper. And then they do see, they do observe for some discrete spin chain systems, they do observe negativity of the tripartite mutual information. So today I want to study these quantities in the context of 2-dimensional conformal field series. Can we detect complex dynamics of conformal field theory by using these quantities? That is going to be my question. So as I said, I can study operator entanglement for the unitary time evolution operators of CFT or many body systems, but it can be studied for other operators, some local operators, for example. I think I will be mostly focusing on unitary time evolution operators, and then I will just make a very brief comment for the local operators as far as time permits. Now I'll be moving on to basically results. So if you have any questions, maybe now it's a good time to ask. Okay. Otherwise, I'll just continue. So here's once again the systems of my interest. So I will be considering conformal field series, but there are various kinds of conformal field series depending on their complexities, so to speak. So in the one extreme, we have something like free fermion conformal field theory that is integrable, and then there's no interaction. So something like thermalization or quantum information scrambling, we don't expect to take place for such a simple quantum field theory. On the other hand, there are other conformal field theories which may exhibit quantum information scrambling. One possibility is the conformal field theory, which admits holographic dual description that can arise in the limit of large central charge with sufficiently strong interactions, for example. So I will be contrasting these two theories, one as a system without scrambling, and the other of which we can expect quantum information scrambling. But these two are not the only possible cases. And for example, we can, in our paper, we also studied compactified free boson theories, which can show the behavior, which is somewhat intermediate between these two extreme cases. But for the sake of time, I will be focusing on these two extremes, and I will just make a comment on the compactified free boson theory, okay, which may have moderate quantum information scrambling, okay? So let's start with the simplest case. So free fermion, oh, sorry, here's some, okay, so there's one slide about methods, which is not super important, but we will be using so-called twist operator formalism developed by Clifford and Cardi. So idea is that we can essentially reduce the calculation of quantum entanglement measure to some sort of correlation functions. And then basically the properties of these correlation functions, in our case, it is either 4-point or 6-point correlation functions. The properties of these multi-point correlation functions determine if the system has quantum information scrambling or not. Okay. Okay. Well, method is not super important. So let's begin with simplest example, free fermion conformal field theory. So if you go ahead and compute bipartite operator mutual information between input and output subsystem, here the plot we get, okay? Here two different configurations, so therefore there are two curves. But for example, let's focus on this purple curve. So for the operator entanglement, of course, what we expect first is that it will decay, it will decrease in time, because as you make your unitary operator bigger and bigger, or depths of the unitary operator larger and larger, the information you input will be spread over the system. So you will start to lose the correlation between input and output. We start with the perfect correlation because at time t equals 0, it's just identity operator. So there's a perfect correlation between input and output. But as time goes by, we will lose this correlation. So the operator mutual information eventually goes to 0, but there's many interesting features in the intermediate time. So for the case of free fermion conformal field series, these features we see, this slope or maybe plateau, they can be just explained by free propagation of quasi-particles. For example, for the case of this purple picture, yeah, so in this quasi-particle picture, we envision the free quasi-particles, they just propagate freely, and then they carry quantum information, but they don't talk much. There's no interactions. So for example, for the case of purple curve, this can be explained by these pictures. So we have we basically load these balls or quasi-particles in the input subsystem, and we let them propagate. So some particles propagate to the right, they are right movers. The other particles propagate to the left, they are left movers. And then we just count the number of particles in this output subsystem. So as these particles start to propagate, and after some time they start to leave from the output subsystem, that's where we start to lose this mutual information. That's where this wavefront reach here. But if I wait a little bit more particles start to escape from the output subsystem. That's where this particle reach at this point. That's why we start to lose more information. And eventually all particles leave from the output subsystem. So that's why we get the zero operator mutual information. Okay, so that's simple enough. There's the similar picture for the state entanglement, but we can extend quasi-particle picture for operator entanglement as well. Okay, so that's like, we want to use it as a reference point where we don't see any quantum information scrambling. Okay. Now I want to contrast this free fermion example with holographic conformal field theory. So that is the result listed here in these two panels for different configurations. Listed on the right are the free fermion results, some of which I already show you. So there's some plateau, for example. If I compare holographic result and this free fermion result, first of all, these two results are dramatically different. For example, the plateau we see here, which can be explained by just quasi-particle picture, it's completely gone in the holographic picture. Okay, so strong violation of quasi-particle picture indicates that holographic theory may have quantum information scrambling. That's the first indication. Another features which I want to draw your attention to are these kinks. So in this plot, operator mutual information decrease, but sometimes it changes its slope. So that's something we call kink. I have a kink here. I have another kink here. Sometimes we don't see a kink. That depends on the configurations. That's a kind of interesting features which we see in this holographic CFT calculations. And I want to compare this with the random unitary circuit later. So just, yeah, I want to mention that now. Okay, so to make a more qualitative statement about quantum information scrambling, I now want to move on to tripartite operator mutual information. So in this case now, I have a two subsystem in the output Hilbert space, B1 and B2. And I have a one subsystem in the input Hilbert space. And for simplicity, I will just take B1, B2 both to be a semi-infinite. Okay, so this extends all the way to plus infinity. B2 extends all the way to minus infinity. Whereas I can change the length of this subsystem A. So the length of subsystem A, I call it LA. Okay. And as I said, negativity of tripartite information may indicates the quantum information scrambling. Okay, so let's see how it works. So first, for free fermion conformal field theory, for which we don't expect any quantum information scrambling, as we already seen, quasi-particle picture perfectly applies. So there should be no quantum information scrambling. And in fact, we can immediately see that tripartite operator mutual information is identically zero for free fermion conformal field theory. That you can check by brute force calculation. But if you just combine what we did for bipartite operator mutual information, quasi-particle picture basically tells you that it's identically zero. Okay, just counting the number of balls, we get 0. So that's good because we don't expect any quantum information scrambling for free fermion CFT. Now, how about holographic conformal field theory? So this is what we get for holographic conformal field theory. So first of all, tripartite operator mutual information is negative for holographic conformal field theory. So that's as expected. We have quantum information scrambling for holographic conformal field theory. We are also interested in the scaling of the negativity of tripartite operator mutual information. So if we focus on the late time behaviors after, so tripartite operator mutual information decrease, and then it starts to develop some sort of plateau. So if we focus on these plateau regions at the later times, we found that this negative plateau scales as the volume of subsystem A. In this case, it's just the length of subsystem A. So so that's a very large number in the sense that if you can make area bigger and bigger, tripartite operator mutual information becomes more and more negative. I will also contrast this with other theories where we do get negative operator mutual information, but it's not as negative as holographic conformal field theory, as it turns out. But anyway, this negative value is almost the maximal possible negative value in the following sense. So tripartite operator mutual information satisfies the simple bound. And if you compare this late time value with the entanglement entropy for subregion A, regulated in a proper way because it's a field theory calculation. So there's some quantity, this quantity diverges. But if we properly regularize, we precisely see that this quantity is -2 of the entanglement entropy in region A. So that's saturate this bound. So that's the minimal possible tripartite operator mutual information we can get. And the holographic conformal field theory saturates this bound. So one could say holographic CFTs are most quantum information scrambling as allowed by this bound. Okay. So I said this is the most negative, but to support this argument, I can also contrast holographic CFTs with other theories. So for example, we computed tripartite operator mutual information for compactified boson theory and the other rational conformal field theories. And for that, we have to focus on second Renyi entropy for technical reason. It's convenient to consider second Renyi version of tripartite operator mutual information because it's simply related to the partition function on the torus, which is computable. So we cannot compute the von Neumann version, but with this caveat, we can compute tripartite operator mutual information for many conformal field theories. So for example, for compactified boson theory, we can distinguish two cases where radius or Rattinger parameter of the compactified boson theory hits some rational numbers, where we see we expect organized spectrum, so therefore perhaps less chaotic. Whereas if you tune radius to be irrational values, we expect more complicated spectrum, and therefore we may have more complex dynamics. But first, for the case of rational radii, tripartite operator mutual information at later time saturates to negative value, but it's a constant with respect to subsystem side. Okay, so we can say there is some small amount of quantum information scrambling, but certainly this is not as big as holographic case, where in holographic case this negative value scales linearly with respect to LA. Okay. For irrational radius, we do get, once again, negative tripartite operator mutual information at later times. But it's more negative in the sense, compared to the rational case, in the sense that this LA scale, the negative part scales a log of LA. Okay, so it's more quantum information scrambling than rational case. But still, it's less quantum information scrambling as compared to the holographic case, because it's only logarithmic. Okay, so that's demonstrate. This is another support that this is the most quantum information scrambling among theories we considered. I think there are also other rational CFT cases where we can relate this rate time values of tripartite operator mutual information to the modular data, but I have to skip this. Okay, so I think another important part of this work is to understand the entanglement propagation for holographic CFTs using Rhine tension picture, which is developed in the context of random unitary circuit. Since the quasi-particle picture does not apply to holographic conformal field theory, we wanted to develop some sort of intuitive understanding for the entanglement propagation or operator entanglement. So we borrow the idea of this Rhine tension picture from the random unitary circuit context. So this Rhine tension picture is described as follows. So in the Rhine tension picture, entanglement, for example, quantum information measure such as entanglement is given by the local integral of some quantity associated to this Rhine, fictitious Rhine. We can associate to the Rhine, we can associate some local functional, which we can call a tension, like energy associated to each Rhine. And the entanglement is simply given by the integral of this Rhine tension. Okay. So this has been tested for some exactly solvable random unitary circuit models, or it was also tested by numerics. So we borrow this Rhine tension picture and see if it can fit with what we found for holographic CFT. So here's what we found. So this is our holographic CFT result. And as I showed you before, there's some kinks where the operator entanglement changes its slope. This is the operator entanglement computed for random Clifford unitary circuit numerically. And then we see structures which are very similar to this holographic CFT calculations. First of all, these two holographic CFT and the random unitary circuit results, they are very different from free fermion result. For example, this plateau is completely absent. But this random unitary circuit also reproduces the kinks, which we saw, maybe not as sharp as here, but we see some sort of kinks even for random unitary circuits. For tripartite operator mutual information, if we compare random unitary circuit and the holographic CFT side by side, the behaviors are also very similar. This rate time value, this is negative, and they scale as the volume of subsystem. So overall, they are very similar. And there's this Rhine tension, using Rhine tension picture, we can now understand where these kinks come from. So if we apply Rhine tension picture for this operator mutual information, And that's how, this picture shows how these lines evolve in time, and depending on the configuration of these lines, and by using this line tension functional, we do reproduce these kinks. Okay.
Can I ask a question?
Yeah, sure.
What's the meaning of the bond dimension in this random unitary circuit? Is it some kind of Cardi entropy or?
Yes, exactly. So that's right. So yeah, short answer is yes. So so yeah, that's something I didn't show you here. So this Q is the bond dimension of the random unitary circuit. So to make a precise comparison, qualitative comparison between random unitary circuit result and the holographic CFT result, we can take Q to be exponential of pi times Cardi entropy. Then we can make a qualitative comparison.
Oh, yeah, thanks. By the way, you will need to wrap up soon.
Yeah, that's right. So I think I'm almost, in fact, done. So yeah, so as I said, I'm a bit ambitious. So I focus on unitary time evolution operators. And the local operator, thinking of time, I will perhaps just skip. You can ask me later if you're interested. But once again, local operator entanglement tells us something about quantum information scrambling in conformal field series. And we can also make a contact with out of time order correlator, which I think I have to skip. Yeah, so here's a summary. Basically, operator entanglement for time evolution operator can detect quantum information scrambling. And for the case of holographic conformal field theory, entanglement propagation is described by line tension picture, as opposed to the quasi-particle picture, which applies to integrable systems. And with local operator entanglement, we can define this statement a little bit more. Yeah, that's all. Thank you for your attention.
Yeah, thanks, Shinsei. We have time for questions.
I have a question.
Yeah, I have a question. Sorry, please go ahead.
Okay, I was just going to say, don't you expect that these sharp kinks are artifacts of large N or large Q, which will go away for finite dimensional Hilbert spaces?
Yeah, so it's not super sharp for, so this is random unitary circuit where bond dimension is 2. So it's not super sharp, but it's still sort of there.
Okay.
Yeah, so I could also mention some features survive even for small bond dimensions, but other features don't. That's precisely the point about local operator entanglement, where for the local operator entanglement, holographic result and the random unitary circuit result match only for large bond dimensions. But for this particular case, we are lucky. We see these kinks even for very small bond dimensions, albeit they are not super sharp.
Shinsei, can I ask a question?
Yes.
Is it for the irrational boson? Do you need the line tension picture, or is it just simpler? Is it more like a quasi-particle picture?
That's a very actually good question. I don't know precisely. In some sense, this is the intermediate case between pre-fermion case and holographic case. So we don't have a super sharp, we don't have a very intuitive picture, but in fact, if we just look at the bipartite result, so this is for tripartite result. If we look at just the bipartite operator mutual information, what you see there is that it's almost like a quasi-particle picture. We see some sort of plateau, but curves are very much rounded. So, but it fails to capture tripartite operator entanglement result. So yeah, is there any good picture for this intermediate case? That's a good question. I don't know.
And another related question: if I take take some spin system which you believe satisfy ETH, then most likely it will go to some volume law with negative sign. But the coefficient of volume law will be the thermal entropy. What do you expect there?
Yeah, so that's, I think we may expect, yeah, actually, I don't know. Yeah, so this is for very small spin chain.
Is it known about the coefficient of the?
Yeah, good question. I don't know. Here it's very close to Haar random value.
Right, but it could be because of infinite temperature state or something. But
well, maybe yeah, maybe this is for small. Yeah, good question. I don't know. Yeah. Yeah.
Okay. U is dominated by the infinite temperature part of the Hilbert space. So.
Yeah.
Can you clarify something about this rational and irrational radius?
Yeah.
So just to make sure that we are on the same page, when you say radius, do you mean radius or radius square?
Oh, that's right. So I think it's perhaps radius squared. Yeah.
Okay. So this is just to make sure that I understand my question. So as you vary the radius, how come the answer depends in such an erratic way on the radius? Because the physics should vary smoothly with the radius.
Yes, precisely. So that's where I have to put this comment for large enough LA. So this LA is chosen such that, yeah, so if you put some radius, there's some, I don't know exactly how to say this, but LA has to be larger than radius or inverse radius, whichever bigger. So we in fact derived a more elaborate behaviors which can smoothly interpolate various radius. But here I take a limit where L is large, super large. So that's why we see these two.
But I'm puzzled. Behavior. The theory is conformal, right? So, so L, we can take L whatever we want.
So here there's some sort of competition between, yeah, that's right. So it's a conformal. So why is there some sort of rank scale? It's perhaps not precisely rank scale, but it's more like a local Hilbert space dimensions. So if, let's say if I had take a irrational boson or minimal model or SU2 level K, whatever, there's some sort of kind of notion of local Hilbert space dimensions, and then LA has to be large enough such that it will not be affected by the dimension of the local Hilbert space. Because if LA is small enough, and if the local Hilbert space dimension is still large, you maybe get some kind of artificial result where we still see some sort of quantum information scrambling, which goes away precisely in this limit if LA is large enough. Yeah.
It's still not clear if LA is large enough, how, as we vary the radius, the answer changes.
That's right. I should also
mention an infinitesimal change of the infinitesimal change of the radius means that all the conformal field theory data changes infinitesimally. How can this thing jump so much?
Yeah. So. Right, so yeah, I'm not sure if I can give you a super sharp answer. Okay, so but I can tell you what we did. So this is something we eventually derived, but before doing this, we just take a torus partition function of the compactified free boson and compute I3, and we just plot late time value. We wait long enough, And then in fact, you get date time value, which changes smoothly as a function of radius, okay? But we see some sort of peaks whenever radius or radius square hits rational value. You see small bump, okay? Then we change LA, so these peaks will stay. But away from the peak, this LA, the I3 or minus I3 diminished to 0. So we can sort of see, so let's say for finite LA, you always get a continuous change for I3, for sure, like you expect. But the way it changes, the peak, height of the peak changes as a function of LA depends if you hit a rational radius or irrational radius.
So you're not surprised that if we take the answer to be the radius squared to be 1 versus 1 plus 10 to the minus 100, the answer is completely different.
Yeah, that's yeah. I mean, if I plot these two results as a function of radius for any fixed LA, you just get a smooth curve. Yeah.
Okay, this is interesting.
Can you comment a little bit more on what you were going to say about the local operator entanglement?
Yeah, so I think it also shows up here, but for local operator entanglement, we can sort of refine what we did. So let's see. So first of all, with local operator entanglement, we now have to say which operator to work with. For the case of unitary operator, time evolution operator, it's almost unique. If you say this is my theory, you have just one time evolution operator. But now for local operator, we have some choice. And the point is that for something like random Clifford circuit, which is not completely quantum information scrambling, we see dependence on the choice of the operator. For example, we can choose to work with local CNOT gate or local Hadamard gate. Then we see different result, okay? And we also see just weak scrambling. So that's something we didn't see here because for the random Clifford circuit, result seems as if it is almost like holographic conformal field theory. But with closer investigation using local operator entanglement, we see Clifford circuit is not actually very strong quantum information scrambler. That I think it's related to the fact that Clifford gates are from a unitary 3 design. So there's some quantities which looks like almost like a random, completely random, hard random circuit, but some quantities which they don't show very chaotic behaviors. On the other hand, for very chaotic systems such as holographic CFTs or hard random unitary circuit, rate time tripartite operator mutual information saturates to most negative value regardless of the operator we choose. Okay, so that's one message. And I should also say line tension picture, even with operator, it also works. Yeah, I can say more if you're interested.
That's great, thank you.
Okay, if there are no further questions, let's thank Shinsei again. And we will see you the same time next week. I'll leave the meeting room open in case someone wants to continue the discussions.